And then
out there, but pretty sure most people like the data science space that I know of like.
okay, so now we should be good to go.
Okay.
And then I'm gonna be really ridiculous and do this.
Okay.
So in the room. Hello. Okay. See, I'm just being ridiculous.
Okay.
Welcome guys. Thanks for coming to the data engineering meetup. I am so glad you made it out here on is it a hockey game or a jazz game thing?
Trans-Siberian Orchestra.
Trans-Siberian Orchestra.
Oh.
That's what you could have been doing in your time. I had a meetup the night of the election. We had a go meetup the night of the election, and the speaker missed it because of the election, and everybody else that came to meet us like, why? Why is it? Because the people that don't go to those things don't care about it. And so anyway, it was funny because the speaker was watching live voting feeds, and we were all like, who cares? It's free. Anyway, this is the data engineering meetup. First off, we need to thank Recursion for sponsoring and giving us food. Everybody clap for Recursion. They do this all the time. I was at CubeCon and we met a lot of people who've never heard of Forge, and they were like, "Do you have any meetups in Salt Lake?" I'm like, "We have one." And so, thanks for being our one meetup that's in Salt Lake. This meetup is also brought to you by Forge Utah. Forge Utah is a nonprofit. We've run a bunch of meetups. We've had an awesome Slack community. If you haven't joined that Slack community, you just go to the website, forgeutah.tech. There's a button right in the middle of the screen that says join Slack. Click that button and then join the data engineering channel. You're there. Really easy. There's another Forge meetup next week. Yes, I know it's Thanksgiving next week, but people really want to talk. Next week is our MLOps meetup, and we have 2 speakers because Mariah double booked. On accident. So we have 2 speakers next week talking about MLOps. One's talking about GPU optimization, and the other one, I don't know what he's talking about. Nobody told me. Because he wasn't the one I scheduled. I have Outer Bounds swag up here. If anybody would like an Outer Bounds shirt, Outer Bounds is an MLOps platform as a service, I think, or something. I don't know. If you're interested, they gave me a pamphlet too. This is their leftover CubeCon swag. They're like, you're local here, take a box. And I have stickers as well. Last note, is anybody hiring that would like to announce that they have jobs? That's our last announcement. I want you to know for the last 6 months, the answer's been 0, so go ahead.
I just learned today that Daxter is hiring for a bunch of different roles. So if you're interested in like sales engineer, platform engineering manager, product manager, like we have a bunch of roles on the website. You can talk to me or refer you.
Oh, you know somebody to refer? You work there.
I work
there. Nice! Congratulations. Go talk to Deep Yana. He works there.
as of today, so like I know nothing about working there, but
he will refer you.
Well, yeah.
I mean, Etsy is hiring, but I'm quitting, so I can refer you, but I'm not going to be there anymore. Basically everything. Search, ads, and Rex are hiring.
Recruiting's still hiring for some really niche roles. We have an IT role for IAM specialists and still high-performance computing storage engineers.
I ran into a high-performance computing engineer from the EU. I said, Recursion's hiring, and then he was thinking like I was crazy. So I tried to get you that job.
We appreciate it. So far, I only have one person on the interview docket. So if you know anyone who specializes in high-performance storage management solutions, please.
Recursion has their own supercomputer.
We do. It's pretty awesome.
Cool. So we'll go ahead, turn the time over to. What's the name of the computer?
BioHive.
What is it?
BioHive.
BioHive? Okay.
Cool. Well, I'll turn the time over to Miriam and let her introduce herself. And
Okay.
we're super excited to have her. She was willing to, I feel like we didn't give you that much notice, so like, thanks for stepping up, I don't know, like a month or something. But for coming and speaking with us. So give a round of applause.
Thank you. Yeah, so I am Murium, and I'm going to be talking about how we generate training data at Etsy. I'll first go over like a very high level overview of what is training data, and then like a few different examples of training data for recommendations retrieval at Etsy specifically, but probably just generally applicable to e-commerce. And then I'll go over like 2 design paradigms that exist at Etsy for generating training data and like the pros and cons between them. Okay, so I'm Murium. I've been at Etsy for about 4 years. I lead the recommendations retrieval team, and I'm a staff applied scientist there. But I submitted my resignation today, and I'm starting at BioRender in about a month. So yeah, I'm not going to be at Etsy anymore. Okay, so what I'm going to be talking about is basically overall, just like this is the life cycle of training a model. What I've done over most of 2023 prior to 2024 was just abstract out all of the pieces that don't need to be changed during model training. And so the only things that you actually need to touch when you're training a model are these samples, which is essentially like what data contains like high signal information about what you want to teach your model. So like labeled data is what we want to think about. And then the other thing that you would want to manipulate is feature specifications. So how do I want to describe those high signal data points to my model so that it can learn the behavior that I want it to predict? A loss function, which would basically be how does the model score its inferences and adjust its behavior to become more accurate? And then a model definition, so which type of architecture do I want to use to learn the behavior? Everything else should not be accessible to the person training the model. So anything around like ingesting types of features or batching out training data sets is abstracted away, connections, integrations between like Beam and like your single box machine where you're deploying TensorFlow to actually train the model should not be accessed by the user. And this abstracted training data pipeline actually caused my team to be in 2020, because I built it in 2023, in 2024, the 3rd highest experimentation volume in Etsy. And no other ML team came close to it. The only other teams that were close to us were just the product and platform teams. So teams that were deploying like UI changes and experiences like that. Ours was the highest throughput of the actual model changes. So the parts that I'm going to be focusing on for this talk are just the first 2, which is like coming up with that sampling strategy and joining to features. Okay, so first I'm just going to talk briefly about what is training data. So the most relevant type of model to think about in e-commerce is usually supervised models. There are also paradigms of like unsupervised and semi-supervised, but I'm not going to talk about those because supervised models cover like almost everything you need to do inside of e-commerce. It's all of search, all of ads, all of recommendations falls primarily under supervised models. There are some things that use unsupervised like clustering and label propagation for semi-supervised, but most of the pipelines you need are supervised training. So for supervised models, we need 2 types of data. One is samples, which is basically a label on a data point that is basically what I want the model to learn. So in the like very naive example that I have up here, these samples are cats and dogs, and I would have many, many instances of cat and many, many instances of dog. And that's the label I want the model to learn. That's it. And then the only other type of data that I need is features. So basically, how do I want to describe what are these 2 types of labels to the model so that it can learn to predict those labels? And it can be things like weight, color, what kinds of treats they eat, that kind of a thing. So a more realistic example for training data at Etsy, the types of labels we want to learn is like behavior, desirable behavior and undesirable behavior on our platform. And the samples themselves are a little more complicated here because they're like a tuple of entities. So you have the user at a specific timestamp because you today is different from you last week, is different from you last month, and what you're interested in on our platform is different in all of those cases. Plus an item, like did you click on an item or did you ignore the item? So like this tuple of objects is actually the sample, and the label is whether or not you engaged. So that's like the type of samples that you can get. And we'll talk a little bit more about more complicated samples in a minute, but for these, like the features can then describe any of the entities in that tuple, including like the timestamp. Like you can say that timestamp exists within a month, within a day of the week, within like the morning, afternoon. You can describe the user as some demographic information that maybe you purchased from a competitor or something, or based off of last actions that they took on your platform or the type of device they were using. The list, like the items themselves can be described with text, with images, with aggregations of the popularity of how popular they are on your platform. So a lot of different types of features can be applied. Okay, so I'm now going to talk about like specific types of samples, which is like the specific types of data we want to draw in that very first part of our pipeline, which is just getting those samples, the labeled data. So labeled data at Etsy can come from like a variety of different sources. The most common one, which is just prevalent in e-commerce, is the visit log, which is just the like the log of all of the events that are fired on Etsy based off of actions taken by users on Etsy's website. This is like a very heavy data set. It's very difficult to parse rapidly. We also have like buyer data, which we purchase from other places. So information about household incomes, demographic information that we can harvest. Then we also have snapshots of just historic data. So all transactions that have ever occurred on Etsy or all favorites. Yes, that is technically a subset of the visit log, but in this format, it's just like a BigQuery table in GCS because we want to be able to access multiple months of transactions at once. And usually we can't do that with the visit log because it's so huge. And then the listing catalog, like all items that have been on Etsy ever. So samples can come from anywhere. And I'm going to go through a specific example here of like a type of sample data that you might want to produce. So say we want to build a complementary model. A complementary model is one for which like we have an item and we want you to purchase another item with it. So this could be used in like a checkout experience. Like when you go look at your cart, we might recommend an item. So you might add it to your cart and buy two. Or if you've just purchased, we might send you a thank you email with recommendations of more items to buy. And the type of model, the type of behavior we want the model to learn here is stylistically similar, but functionally different. So it's like a pretty nuanced idea of like what is true behavior, that like desirable behavior. And the naive solution would be to just look at all of our data and find users who have made multiple purchases across different categories and be like, here's your training data set. But the problem there is like the data gets very, very sparse. So what you actually have to do is like come up with ways to fabricate your data so you can increase the volume, so you can actually train a model to learn this behavior. So a very common way of doing that is actually learning relationships between the categories at the category level first, and then propagating them down into the listings so that you can like sample up. So an example would be like, we learned that coffee tables and side tables go together. So we can find items that have either been, are sold by the same shop, have similar attributes, and then create fake training data that way. So that's one way that we might want to generate those samples. Another like strange situation in which you want to generate samples is like trying to learn long-term user behavior. So in short-term models, you can basically just harvest in-session data and like try to create like a click hole behavior and just like get the person to click until they purchase. But when you're looking at like a long-term user behavior, try to get them to engage, it's like a repeat visitor. You need to be able to identify training data that exhibits like new mission behavior. And so you're going to want to look at things like users with activity gaps who come back and like start engaging with a new category, or users who purchase and immediately after they purchase, they start engaging in a new category. And those can be estimates of like new user behavior, or people who come from like external ads. we can use those as like new mission. This is a little more challenging than just accessing the visit log, because you actually have to track the user's behavior across multiple weeks and then aggregate it somehow. Okay. So the other thing that is useful for knowing when you're using sample data is some samples are just kind of noisy, and so you want to refine them before you pass them to your model. An example would be like denoising samples based off of dwell times, and those thresholds could be different for different parts of your website. We might want like a lower threshold on like a checkout experience because there isn't a lot to distract the user. There's just like one recommendation. They either clicked on it or didn't. It's probably high quality if they clicked on it. You might want a longer threshold. Yeah. Yeah, so if I click on something on our website and I close the website or I take a different action, the time from when I landed onto that page, the results, versus when I took the next action, the time in between those is considered the dwell time. Like how long did I stay on that page? So we usually use dwell time to like, it's also called long click, but it basically denoises your data set. But different thresholds might be applicable in different parts of your website is basically what I'm trying to say in this slide is just denoising it based off of the information that you have on where the link was displayed to the user, how much noise was it around it to distract the user. And that can change how you do your samples. Okay. So the other thing that we want to talk about, because like all the things that we talked about so far were like positive behaviors that we might want to sample. There's also negative behaviors you want to sample. So sometimes like the model can learn patterns you don't intend for it to learn. For example, like maybe all of the listings from the same shop have some commonality to them, and the model is just going to start thinking that that shop is relevant to the user rather than the actual user's preferences. So you need to be able to harvest negatives from the same shop that the positives come from. So your sampling strategies to pull data for negatives can also get pretty complicated. Okay, so this is these are just all the sampling strategies that we've that are actually used at Etsy right now by my team. If any of that didn't make sense, let me know. If not, I'm just going to talk about like how we actually generate those out of the visit log then. Okay, so the visit log is the largest data set that we have. You cannot usually aggregate multiple days at once. You have to come up with some way. It's actually parsed out by hours. So if you want any of the kinds of behaviors that I just mentioned, which is like goes across days and calculates across users, you need some way to like break up how you're accessing the data because it's just too high a volume of data. And then you can actually generate labeled samples. So there's actually 2 paradigms at Etsy right now on how to do this. One is a shared pipeline via front filling, and one is a project-specific pipeline via backfilling. So what do I mean by front filling? Front filling is as soon as a user makes an engagement on Etsy, we assume that that is going to be used to train a model. So all actions on Etsy are now assumed to be training data for some model. And then what we're going to do then is like we'll use the existing logic for labeling. We'll have some predefined logic for what is a label. And then we're going to use the union of all models trained off of this data set, this like that are currently used at Etsy, to decide what features to join the data, join against this labeled data. And then we're going to store that as pre-trained data. And all of the downstream models are using just this shared data object. And then we accrue training data over time. So this is like front filling. We don't actually ever run a backfill. As you go, you accrue training data, and that's it. And you assume all actions by the user are going to be used by a model at some point. And then the project-specific pipeline, which is the one that I use on my team, it's after a user has engaged on Etsy, your data is living within the visit log at some hourly rate. We can parse the visit logs by dates and by hours. And then for each model, we come up with some logic, like we just said, for how we want to label the data. And we write a job to filter just to the events that you want. And then we join just to the features that you need for your model. And we only backfill the necessary training data that we need. And then we can build the training data as it's needed, only as you need it. And it takes about an hour to backfill like a month's worth of data. And Etsy has pretty high volume, so it's a lot of data that can be parsed quickly that way. Okay, so why is it that we have these two different paradigms? I mean, there's obviously trade-offs to every system design. So the pros and cons of the shared pipeline is that science users who are actually trying to build models can immediately jump into model design. They don't have to do anything prior to building a model. They can just immediately start building a model off of data. It already exists. And it doesn't require them to have any knowledge of the data or the ML ops for upstream data from them. They can just assume that they have the data that they need and start building the models. And it's very easy to analyze their trained data because it always exists. It's always there. The cons are it's entangling multiple processes together. So it's entangling access and parsing of the visit log. It's entangling labeling and sampling the data. And it is entangling feature joining all into one giant process. It introduces a single point of failure into our data pipelines. And this has gone down like multiple times when I've been on call. And it affects like every downstream model, like search and ads and recs all get affected when you do it like this. There's no clear owner because the single job requires knowledge from ML ops, data engineers, and data scientists to actually maintain. And there's no separation of concerns, so single files are edited by like all different teams. And you can't easily edit the pipeline without like having massive effects to all downstream jobs, which has also happened to me. Like someone has just changed training data out from production models and we don't figure it out for 6 months because data failures are often silent in models. So your model will not give an error. It will just produce incorrect predictions for users and continue to do so until someone complains about it. So you won't detect failures. And the storage costs are insanely high. We're taking a union of all features used across all the models. A lot of that is just like text descriptions of products joined over and over and over and over again. And like the popular items text descriptions are just getting joined to the same data points like billions of times every day, which is, in my opinion, ridiculous. Okay. So, I mean, clearly I have a favorite. So this is the other option. The pros of it is each project is decoupled from one another. The only single point of failure in a project-specific pipeline, which I also like to call run each time, is the visit log itself. If the visit log goes down, it's the only time where you can have cascading failures that affect the entire system. The storage costs are incredibly low because you can filter early, filter often. You only store the data necessary for each model. You don't need to do a union of anything. Each platform team knows exactly which piece they support because you can actually modularize out the access to the visit log, which I can show at a future slide how we did that. And it's easy to make changes to any part of the modularized pipeline. So if I want to change out data sets, or what actually happened is like someone built a new feature joiner, I can just pop out the feature joiner from my pipeline and put in theirs, and I can immediately be on the new feature joiner. So my team was like my team is always the fastest on migrations now because our pipeline is decoupled and there are pieces that can be popped in and out. Whereas the other pipeline is one giant monolith, so you have to change the entire thing every time you want to make one change. If you want to touch a single component, you touch all components. So the cons are that each project does require its own training data pipeline prior to a scientist being able to build a model. It also means that the scientists have to have knowledge of how to navigate our data pipelines, how to use Spark, and effectively write their own pipelines. So it requires them to get comfortable outside of just TensorFlow. And there are operations that are repeated across pipelines, and they're recalculated over and over. So for example, I might be accessing the clicks on a certain module over and over and filtering to them. But these are actually pretty cheap. And I do want to point out that this idea of rerunning calculations rather than figuring out how to store and exchange data is actually how the LLMs became super prevalent. They created something called flash attention, and flash attention is purports that you can recalculate things rather than propagating around giant matrices of gradients. They just recalculate it in place over and over. And that's kind of what I'm saying here in an entirely different system. Rather than trying to figure out how to propagate around joined feature training data, just recalculate it in place and only save what you need. Okay, So the training data paradigms at Etsy, you still have the shared training data pipeline, and then we have the project-specific one. On the left side, the shared data pipeline, all projects have to use the same labels. That means if anybody wants to change labels on their model, which there are projects on my team where one person's positive is another person's negative, they can't do that on that model because it's a shared labeling strategy. On the right side, you can pick your own labeling strategy dynamically. On the left side, the modeling teams directly read from the visit logs because there's only one giant pipeline. I don't know about you, but I don't trust like myself, who specializes in models, to know how to correctly parse out a visit log at like high volume. So that scares me. Whereas on the right-hand side, I don't access the visit log directly. I access it via a layer owned by the data engineers. At Etsy, unfortunately, search, ads, and Recs all use the shared data pipeline. Only the teams that I interact with and lead use the project-specific pipelines. So the major thing that is different, though, on the shared data pipeline, logic is shared as an artifact, as a Parquet artifact, a giant Parquet artifact that is built over time with features joined in. On the right side, there are no shared artifacts. Instead, code is shared. And like my argument here is that if you're using data, you shouldn't share the actual data. You should share the functions that are used to engage with the data. And that's kind of the paradigm that I'm trying to popularize at Etsy. I don't know, maybe other people don't have this problem. Okay, so how was I able to create this like backfilling access layer? I ended up negotiating like a two-part access layer to the visit log. So what I ended up doing was, I guess the feature joiners we'll talk about later, because what we've been talking about so far is just how to get the samples. So what has happened now is there's a data engineering team, there's an ML engineers team, and there are the scientist teams. The data engineers, ML engineers, and scientists all engage with one set of files and functions, all combined together in the previous paradigm. In this paradigm, the data engineers only own and optimize the access layer against the visit logs. They don't have to engage with like the calls to this that produce a data set, and then the data set becomes this like shared object. They don't have to worry about Airflow pipelines that are generating data sets. They're only optimizing an access layer. The calls to it are then owned by my team. So ML engineers and data scientists own the actual calls to it to produce labeled samples. So we've like separated the concerns that way. And what we own is not, so what they own is how to engage with Etsy events that are fired off of Etsy Web, how to update those events, how to parse out specific entities and fields from those events, and how to scan multiple files across multiple days efficiently, how to do sampling if you have user IDs specified, if you have session IDs specified. All of those things are owned by them. What my team owns are reusable functions for pulling page-specific actions, or functions for applying different types of dwell times across different types of days, reusable functions for like different types of ref tags we might want to use, like what is considered like an external landing or an advertisement. And then we have the next step that we'll talk about, which is like the feature joiners. And these are owned by the ML ops engineers. Yeah, they have pipelines with specifications on features to join via timestamps and functionality for defining types and maintaining them. So basically services that if you engage with them, it returns you a feature spec with the type specifications in it, so you can connect your data into TensorFlow. Okay, does that make sense so far? Okay. So this is just like a more code example. Basically, the visit log is being all the different types of events that are firing. And then we have the training data set reader, which is owned by the data engineers, that produces that produces a set of filters, not a data set, but just a series of functions. Then our team calls those via sampling logic to produce an actual sampled training data set. So the data engineers are not responsible for producing the training data. They're only responsible for maintaining the functions for which can be used to produce the training data. Okay. This is just very Etsy specific code because this is a presentation I just gave recently at Etsy. So this is just the code, but it shows like how simplified files for our training data are, because we're calling abstracted out functions. The other files at Etsy are like very, very long with like very specific, like many lines of just accessing, parsing out the visit log in place in those files. So that's literally all we were trying to show here. Yeah, I only use Scala, Spark, and TensorFlow. That's it. Scala, Spark, and TensorFlow. Why? I didn't know Scala. It didn't mean I didn't like it. I wanted to learn it. I asked. Yeah, I was asking for like Scala resources so I could learn it, and then I learned it, and then I used it. Oh, okay. Okay, yeah, so this is just to like reiterate to the audience at Etsy that like, I promise you the data set is still the same regardless of the process that you use. You still end up with user IDs, listing IDs, labels, and timestamps. I'm not giving you different data. Okay, so that's up till now how we do labeled samples. Now we'll talk about feature joining. We have replaced my feature joiner with a dedicated one owned by the MLOps team, which is a lot better than me maintaining it. Okay, so how is feature joining different across these two paradigms? In the shared pipeline, you don't have to keep track of features as they change because you're joining them as they happen. So it doesn't matter if a feature changes, I just pick what its current value is and join it into the training data. But I end up using like storing extra features because each action that a user can take basically could possibly become a training data sample at some point in the future. So I'm just storing a lot of extra data anyway. The backfilling pipeline ends up having a change log of the features. So this is important because remember when I said like a lot of the features that are really heavy are just like the text descriptions of listings or items. Those do not change. We're just storing them over and over and over. And so when you just keep the change log of those features, it actually becomes a lot smaller. You save space because I'm not writing the same thing over and over. I'm only writing it if it changed. But you do have to maintain functionality to join the latest relevant timestamp for that feature. So if I passed a timestamp from 2 weeks ago, you need to get the timestamp that occurred before 2 weeks ago, but is closest to 2 weeks ago. So there's a little bit of extra logic on the joining. Okay, so ultimately, we just need like offline feature fetching. And this was like previously pretty difficult to do to get the correct line up the timestamps. We now have a dedicated team working on that. It's part of the reason why Etsy, like the front filling system became so predominant at Etsy, because figuring out how to do that join and getting like dedicated workers who work on making sure that join is working correctly was very difficult for us. The actual joining functionality, the feature joiner, they named it Time Machine, but it provides flexibility in that you can get the correct feature values for any entity ID and timestamp combination. It keeps feature joining separate from the logic of label generation. So these are now two different functionalities owned by two different teams, and they are not entangled. And you can mix and match as you need. Together, when you combine those together, you can produce any training data set that you want. Okay. There are challenges in feature joining generally. Like I said, a lot of the features are static. And there are still manipulations we're struggling to match between training and inference. So even though the training pipeline is stable, the inferencing pipeline, it is difficult to match all the same functionality there. The most common one that we struggle with is time-based filtering. If I only want to look at your session-specific data, sometimes I end up with older data, unless I replicate that filtering logic somewhere in Etsy Web. So right now we're actually replicating code around in places and duplicating it, which is not something we want. And we're duplicating it across languages. So like in the training data pipeline, it's in Scala. Once it goes to Etsy Web for inference, it's in PHP. So it's pretty nasty to have that. So we've created a new module called Patina, which you can register those kinds of functions, like filtering logic, into those, and it should be able to call it both at training and inferencing. Defaulting is the other one that is really challenging. The data pipeline, so Defaults are specific to a model. You can either apply them as part, there isn't like one set way to apply them. You can force TensorFlow to become aware of defaults, but this is considered an anti-pattern. That would mean every time someone calls your model silently fills in missing data. We don't generally want that. You can also add in defaulting into your feature layer, but then you have to match a spec of your, during inferencing between your features and the default and the model that's being called. Or you can do it the way that we do it, which is terrible, which is we duplicate the code for the defaulting once in the training data pipeline and once in the inference pipeline. So yeah, I haven't seen a lot of great solutions for this other than duplicating code. Otherwise, you end up having situations where your model is doing weird stuff and you aren't able to do it, because if you force TensorFlow to default, it will not error when you do want it to error. Okay, so those are the challenges in feature joining. To get around them, we do duplicate code. To do that, we basically add a feature adapter layer. When you have a TensorFlow artifact, you can actually add another layer onto your trained model artifact that does some data processing. That's where we're duplicating code right now. So we create like a lightweight, what is technically a TensorFlow layer, but it's just like some filtering logic, and you wrap it around your model, and then you deploy that entire thing to TensorFlow serving. That is the cheap way that we have been doing it. So yeah, that's where we're at that. This is just more example code. Okay, so wins we've had with the strategy. I don't have it in this slide, but in 2024 in H1, the projects that I led, not just my team, but just the projects I myself led, had 50 million incremental GMS annualized across 3 different tracks. And the reason was I feel like we could just iterate really rapidly. We could try new features on the fly. We were able to get support from data engineers very rapidly because they owned certain sets of functions and we owned different sets of functions. They don't have to dig through model code to figure out how to support us. We can backfill a month's worth of training data in an hour. And usually you only use like 3 months of training data to train a model. So within 3 hours, I can generate an entire new training data set. And yeah, we filter early, filter often. The user models with page-specific sampling has been really nice because our platform teams or our product teams are changing the UIs constantly. And if you use the old training paradigm, it's very specific to the name of every single module. So as teams are iterating on the UI, your data is becoming stale and outdated, and then someone has to go in and change it manually every single time. Whereas here, it's just abstracted away, which is pretty nice. Getting all kinds of like strange co-click behavior, building out like click graphs has become super easy. And then I think, yeah, we can just adopt like new data sets as like different data engineers produce them, just plug them in as a new data source. The only other thing that I would talk about here is like the idea of a sequence model. So a sequence model in recommendations is very different than an LLM. In recommendations, the sequence is actually just the user's behavior. So whatever actions you have taken on the platform is the sequence that I'm trying to learn, and I'm trying to predict the next item in that sequence. So basically, you become a sentence, and the words of your sentence are the actions you took on Etsy. And I want to figure out the next action you're going to take on Etsy. What becomes weird here is your sequence the sample or is it the feature? And so that's kind of like a weird toggling behavior. You can actually do both right now in our system, and we want to force people to only do one because we don't want to have multiple ways to do the same thing. But currently, this is like a weird situation where it's like, is that a sample or is that a feature? Not really sure. Okay, and yeah, that was everything I wanted to talk about.
Anybody have any questions?
Yeah.
Yeah, so you mentioned front filling earlier, and where you basically treat all data as training data.
Yeah.
Where do you store all this? There's like a huge amount of data. Where do you store them?
In GCS, and we pay a lot of money for it. Like, I'm not kidding. We have basically 6 months worth of data, all joined to features that just sits like that, and we pay tons of money on it.
So what does GCS stand for?
Google Cloud Services.
Oh, so which service particularly?
Probably the cloud storage service.
Yeah, we pay Google. It's a it's Google's own cloud service.
Oh, like Cloud SQL is, you use that too, or?
I don't use SQL, but Google's SQL Access is, I think, BigQuery is mostly what people use. I don't use it myself.
It's just S3.
Yeah, exactly. Yes. Yeah.
The front filling approach that you mentioned, like it sounds kind of like a roll your own feature platform, feature store sort of solution essentially, except I guess you're storing join data instead of storing each of the features separately and joining on people time.
Yeah.
So, like, do you think like some of the challenges come from this system, I guess, like kind of growing organically? Like if you were to architect as like a feature platform or use more like an off-the-shelf feature platform, like would it still be better to have your project-specific pipelines?
I think so, because the front filling, you can't apply filter early, filter often. Because if I filter any, like all data is considered possible training data. So I literally cannot filter it. What's ultimately happening is I'm replicating the entire Etsy visit log, but I am also replicating in a way that is easier to read for a human and also has all of the features joined to it, which is like so much data. Yeah.
So it kind of, on the backfill pipeline, project-specific pipeline, you had like project separations of concern, the only single point of failure was, I mean, that's all sounded better to me from an ops engineering perspective. But then in the cons, you had each project has to do its own training pipeline.
Yeah.
Why? Because that sounds like a pro to me. So why is that? Why is that?
Because I also think that that's a pro, because it forces people to think about their data before they use it rather than making assumptions. But at Etsy, that's considered a con. I don't know why.
I think from a design perspective.
Yeah, and I templated out all the Airflow DAGs, so you don't even have to write the pipeline from scratch. You have to call a templated Airflow DAG and pass it parameters. I don't understand.
Because data scientists don't want to write Airflow. Is that
I
why?
think that's literally, yeah, they just don't want to write more DAGs.
Oh.
It's like very little, like I showed you, it's like tiny amounts of code because everything is like, but like, yeah, then it's like, oh, now there's another DAG to worry about. So yeah, sorry.
In a sense, who doesn't want to like just have the data magically there, right? Like computer, but I think that's why it's not just there.
No, that's
Yeah.
because I'm building on a system where everyone has to train the project. I want to know what kind of pushback we would get.
It's too hard.
Yeah. Yeah.
Huh?
So comparing these like two options, what were the impacts on inference time?
Oh, the inference time doesn't get affected at all. This is just training, because at the end you end up with the exact same model artifact.
So you weren't like, when everyone was sharing features, like having them also kind of share the features at inference time?
So yeah, they weren't sharing the features at inference time. So instead of filtering early, they were filtering all the way at the end. So once the data is all populated with all of the features already joined, then after it's like sitting there and I waited for it to accrue. So if I was going to train a model off of 3 months of data, I wait for 3 months of data to accrue. Then or maybe it was already accrued because it's all magically there. Then I filter to just the behavior I want and just the features I want. So that's when the filtering happens, all the way at the end. And that's kind of why I feel like it breaks the filter early, filter often paradigm. I feel like I didn't answer your question.
So that's for preparing the training sets, but like, how are they being calculated when they're actually like up and running?
When they're up and running, so your TensorFlow serving model, we wrap it in a layer called Barista, which then queries the model signature to learn which features were actually used inside of that model. And then only those are fetched during inferencing.
So even when they're sharing features, like each model would still recalculate.
Yeah, but it would be like after the data is there, then just the training artifacts are aware of which features to select. or like the model artifacts are aware of which features are associated to them.
We just adding on to that question, like, so, okay, the model artifact knows which features to compute, but like, how are they computed using the same logic as part of, like, or is it using pipelines, or is it like an inference pipeline, and then like, is it computed like multiple times?
So yes, so there are different parts of the pipeline that are deployed. So the parts that I'm talking about are sampling strategies mostly. So I never actually spoke about, why is it so blurry? Let me go to the earlier slide. Is this less blurry? No, right? I don't know what happened. Okay, well, it's a little bit bigger, but okay, so the parts that I think you guys are wondering about are these, like the pre-processing the features for the model and the training of the model. Up till here is just joining features and picking samples. So we don't pick samples when we deploy the model. We just assume that all the traffic that comes in is a valid inference sample. And that the Etsy web knows which samples to pass to which models. And so the logic there would be like, if you go to Etsy homepage, the models that get called on that page are like the user to listing, personalized candidate set, the listing to listing candidate sets. And so there's logic there to call which models to fire off of that page. And so that becomes the sample. The sample at inference time is like which model is called in which placement on which page. So we don't have to worry about any of the sampling logic that I wrote here. All we have to worry about is how we take the features in the signature and process them for model inferencing. And that's where we get this slide. Sorry that I'm like running through the slides again. We basically wrapped those pre-processing layers against the model. Does that make sense? And there, even for this, there's in TensorFlow, there's two ways to do it. One is just to use pure Keras pre-processing layers, and one is to use TensorFlow Transform or TF Extended, in which case you would use Apache Beam to do your pre-processing and training, and it would produce this layer, and then you wrap the two together for inferencing, and you still get the same artifact either way.
That just went over my head. Sorry. You said Apache Beam, and I'm like, wait. Anyway, sorry. If that's it.
Oh, I think Adam has a question.
Yeah, sorry.
Sorry, Adam.
I'm just kind of curious, what's the experience of Patina like, and how do you share these things that you need to in a team?
Yeah.
Like when you've got the separate concerns and things like.
I did not build Patina. I put in a request for Patina, but usage of it has been pretty nice. So it is. You have to register a function to Patina, and then you call the Patina function both on training and inferencing. The hard part is you have to decide what lives in that layer and what's going to live closer to your model. So it does require like a little bit of forethought and planning before you build your model, but it just makes it. Before that, we were literally having issues where like model name, like feature names weren't lining up, and then features weren't being passed to the model correctly. Things weren't being filtered correctly. We had a situation where one filter during training was filtering from the right-hand side of the list, and during inferencing, it was filtering from the left-hand side. And we're like, why is this so weird? I don't understand. And it's like it took us, like, again, these like data pipeline failures are silent once they go into production. There's no way to catch them. So like, it took us like 3 months to figure that one out.
So like the scientist would sort of generate the request, and then like a data eng does the function addition and registration or something?
No, so the way that we built it is like the underlying function that connects with our feature stream is owned by ML Ops. I don't engage with the feature stream. I shouldn't be touching it. What I do is I register functions to Patina, and they own calling Patina both through Time Machine for feature joining in batch or offline, and also integrating that with our real-time feature system so that that function that I registered gets called, integrated into the correct places.
Sorry, so are you basically saying so you can share the same logic offline and for your on-demand feature set?
Yes. Yeah, exactly.
Oh, so you're just sharing the function across. You're just registering the function and sharing.
Yes.
Well, that's cool.
Yeah.
Okay.
And it lets you do things that like TensorFlow genuinely is very bad at doing, which is like being taught, like focusing its features off of time, right? It's assuming that you passed it the correct features. But if you don't do that, then you are building what would essentially be like architecture around feature manipulation and orchestration into a TensorFlow model, which is what I see happening a lot in industry. And I feel like that's a bad design pattern because TensorFlow isn't built to handle those things and it is not built to throw errors in those situations.
I didn't really understand that part. Are you basically saying there's a data contract? So you just implement it with these, I didn't know what those tools are. You just said, this is what our data should look like. For a data scientist, do you have to be more in depth with that and say like, this is what's considered like programming outliers, get rid of that. So like, and then God knows what if you're doing text, because it's the text part used.
Not
Or is it just like
it's
certain values that you only accept?
so text manipulations are usually considered tokenizers, and those TensorFlow does very well. So those are built in. The kinds of things that are biggest concerns are like being aware if the feature list that is passed to the model is increasing in time or decreasing in time. So is the left side the most recent or is the right side? And those are the kinds of things being built into the model. And that's kind of thing. And then it needs to know how to filter back to just 1 week. So now it has to keep it takes an extra feature of timestamp that matches the exact same length as the features. And it can line up the timestamps to the actual features and filter the features off of the timestamps. And that's what what I personally would consider a feature orchestration, but it's being built into a TensorFlow model.
Okay.
I feel like I didn't answer your question.
Yeah, it did. It's just coming from the engineering side, so the data science side will just come at me hard and fast.
Okay, I'm sorry.
I just one other question, since you mentioned that you have the real-time data stream, but you're also applying the same feature logic, or the same like logic that you have for features too. So then like, if multiple models have the same, like if they share feature logic or like a feature computation on the real-time side, is that computed multiple times, or is that?
Yes, even in like any like feature manipulation, regardless of which system you're using, at inference time will have to be called every time a model is called. So it will always have to be recomputed. But they're usually things like filtering logic or like sorting logic. Those are the kinds of things that we're doing to our features. Did that, like, the savings aren't so much on the inferencing side as they are on the training side. So the way that you would get around that on inferencing would be to cache the results from the models. And Etsy is building some caching logic, but it is not common at Etsy. At Etsy, we just recompute every single time.
Well, thank you so much. That was great. We've got